So I need to characterize a motor that I don't have the data for anymore. I've got this little Sanyo Denki motor. I know it's a Sanyo Denki because it looks like one. But it got really hot and the label peeled off the side, so I don't really have the data anymore. The one thing I can do is measure the diameter of the front plate. That is 40 millimeters. That will help me look up in the documents what's going on. I also see that I have a battery here connected to a pink and a purple wire, so it must be an absolute multi-turn encoder. The connection was already done, but I'll show you how I found that. Motor power wires, wire in a logical manner. UVW, white, red, black, or white, black, red. Whatever the standard is, stick to it. Make it logical. And then earth, goes to the case. I got 24 volts here for keep alive, a stove plugged in, and a serial connector with a B&B USB to serial adapter so I can talk to it. Oh, and I have my little engineering book because I need to figure out the inertia of the shaft of the motor, so I'll use some kinematics and Newton's second law to do that. But the first thing we can do while the drive is disabled is measure the winding resistance, because this will help us tune the current loop. 22 ohms, so that's sufficient to get started. If I had an inductance meter, I could measure the inductance, but I'm just going to guess. I'm going to say 10 millihenry. We're going to tune the loops anyways, but that's a good starting point for guessing. So by looking up Sanyo Denki and brushless and absolute encoder, I found a picture that looks similar to my motor. So I'm going to say it's probably a SanMotion R series with absolute encoder. And there's a pink wire, so when I look up pink in the manual, I can see that, yes, in fact, there's a battery connected to the pink and purple, and I've got some data going back and forth with the brown and blue, and +5 and ground for the black wires. This is the absolute encoder. So here's the battery backup absolute 17-bit single turn, 65536 multi-turn. We can also see information about the R2 series. I'm not sure if it's a AA or EA, 200 volt or 100 volt, but I see this size, so it's 04. The watts I'm not sure about. F, no break. P, standard. UL, I'm sure, so that might be the part number. So I'm connected to a new drive. Actually, it was an older drive that I had been using. I created a virtual amplifier for XEC, saved the settings of the defaults as a factory file, and then just reloaded it and saved it to flash. So now when I power up, it looks like a brand new drive. So I'm going to change the settings. It's a brushless rotary. I've got an absolute encoder. I'm going to start off in current mode because that's all I really need to characterize this motor for starters. And emulated output's cool, not that I'm going to use it today, but I like it. So we have some default settings here, so I'm just going to enter some information about this that I know. So I put question marks for the part number that I don't know. The inductance and resistance, everything else is default. On the feedback tab, I entered 17 bits for single turn, 65536 for multi-turn. And I'm going to calculate initial tuning parameters for the current loop so that we can go ahead and start tuning the current loop. So for tuning the current loop, we'll need to first make sure the drive can be enabled. I'm going to spare you all the pull the enable 1 low, clear the motor temperature sensor, and enter the stow. So all these things have already been done here, so the drive can be enabled. So for the current, I'm going to use the auto setup checkbox, hit start. This is a small signal. I'm going to do the 0.1 amps. That's a little bigger, yeah, out of the quantization. So already the current loop looks like it's sufficient. So I'm going to say we're done with the current loop for now. We can go back and check the bandwidth later. And that's just based on entering 20 ohms and guessing at 10 millihenry. That's fine. The next step is to try to phase this thing. So I'm going to enable with 0.1 amps and rotate forward and reverse. They're going in opposite directions. Also, I want to figure out the pole count on this motor. So I'm going to invert the motor feedback, give it 180 degrees of offset. And yeah, you can see they're diverging, so the pole count. So the black is the current vector, and the motor is going to start off in this position. I'm going to rotate it some number of times until I see the motor rotate once. So the current vector is going to rotate 1, 2, 3, 4, almost there, and 5, 1 rev. So it's a 10-pole motor. So twice the electrical cycles is the pole count. Yeah, some minor changes there. So let's go back in and fix this pole count. It's a 10-pole motor. Yeah, we can recalculate. I haven't changed any tuning. So before we try to run this motor, we're going to check the manual phasing again, make sure everything looks hunky-dory. So forward, reverse. Let's try inverting some things. Oh, here we go. Forward. All right, let's make sure counts go up when I go forward. Yes, they do. Everybody gets a chance to deliver current. A little lag in the feedback red indicator. I'm phased properly. So motor phased. Now, a little trick that we're going to do in a current mode is see. So I've got 164 volts and I'm going 4,400 RPM. So 165 divided by 4.5 kRPM equals 36.6 volts per kRPM. And we can enter that data in here. Volts per kRPM. If I change to volts per radians per second, this is an approximation of the 3.5. So 1 Newton meter per amp equals 1 volt per radian per second. If I have, if it's a 1 amp motor, then I would have 0.35 Newton meters per amp. And we'll just give it double that for peak. Everybody should be able to do 6,000 RPM. Oh, that's another good point. If the volts per kRPM is 36 volts per kRPM at 165 volts and I could only go 4,000, maybe this is a 200 volt motor. So that's more data that we have. I haven't calculated the inertia yet, but we'll work on that next. So we'll calculate initial tuning values for the velocity loop. And we'll stick it back into a velocity mode of operation. Oh heck, let's just go for position. Finish. Okay. So tuning the velocity loop. Auto setup checkbox. And we'll knock this. Don't want to go too crazy fast for acceleration. And let's look at the current, actual current. And let's do 3 hertz, 300 RPM seems reasonable. And we'll bang it back and forth here. There's no gains for the velocity loop. Let's give it some proportional and integral. I'm going to find the point of oscillation. there's the oscillation. Oops. And a little more integral. And that looks pretty good. It's a little buzzy. But we're doing this without the calculated values. We haven't determined the inertia yet, but we're still able to tune the velocity loop. And let's look at the position loop here. Give it another few revs. Oh, auto setup checkbox. So, wow, that moved pretty nice. Not too bad. I'm going to say we're done characterizing this motor, but let's work on the inertia. So to determine the inertia, I need to look at the kinematic rotation acceleration. I've got some Newton's law here, some conversion units, and bottom line, the inertia equals the torque divided by the change in velocity over the change in time. So let's see what that is. So I'm doing a current command with the function generator, step forward, step reverse, giving it 1 amp for 10 milliseconds. And we want to see if we apply a current, which on a torque produces an acceleration over a period of time. It looks pretty linear here. So the velocity, actual motor velocity, the change in motor velocity is a 1,304 RPM, and the time is 4 milliseconds. So the torque for 1 amp was 0.35 Newton meters per amp. 1,304 RPM times 2 times pi divided by 60 divided by change in time. So let's see, that equals 1 e minus 5 or 10 e minus 6. So that's a good guess for the inertia. So we will enter that. Kilogram meters squared, 10e minus 6, enter. Kilogram centimeters squared, 0.1. Alright, that's a rough estimate. So looking up the 40 millimeter motors, 200 volt winding, because we need to go 6,000 RPM or faster. Yeah, so you could do max speed of 6,000. So this is the, looks like the winding here. The resistance is 9.3. We actually measured 21, so that's the resistance of two coils in series, approximately. The inertia, I had a 0.1. It's got a 0.06, so mine was an estimation. We also have the torque constant, Newton meters per amp, RMS, 0.42, so I made a small correction there. They give back EMF in millivolts per minute to the -1, so that's in human. So we'll just use the constant there. We've got a peak torque of 1.8 and a continuous stall of 0.31, so things have changed a little bit in our motor data. As you can see, the RMS is 0.42, so, but in peak it's 0.31. I copied that over to the volts per radians per second, so a slight change in volts per kRPM. 0.1 is okay, but 0.0627 is more accurate. 10 poles, peak of 1.18, continuous of 0.13. Calculate new tuning values, and then we can go through the tuning again. The advantage here is that we've got some good values for the peak and continuous current to protect the motor, some initial tuning values for the velocity loop. So you can see the calculated values are pretty close to done for the velocity loop, and for doing a position mode move we should have similarly good tuning based on the calculated values. We can go in and